Okay, so now we can look at a question down here. Chlorine gas reacts, so I'm on number 4. Question number 4. Chlorine gas reacts with potassium iodide solution to produce solid iodine in a solution of potassium chloride. So chlorine gas, when chlorine is a gas, it's in the Cl2 state, right? It's in its elemental state. Reacts with potassium iodide, that formula should be Ki, to produce solid iodine. Again, iodine is one of our diatomic. Oops, solid, not gas, solid iodine, in a solution of potassium chloride, so KCl. All right, write a balanced chemical equation for this reaction. Okay, so our old way of balancing would be Cl2, I need 2 of those, I'll put a 2 here, I'll put a 2 here, and they're balanced. Okay, done. Write the net ionic equation. So in order to write the net ionic equation, I'm going to separate all the salts into their ions. Chlorine's not a salt, it's an atomic state, so it doesn't get separated. 2K pluses and 2I minuses, because those will separate into their salts, or to their ions. Iodine is in its atomic state, so it stays as I2. And then KCl is a salt, so it's going to be K plus and Cl minus and 2 of each. So the ions have everything's been split up. Let's cross off what appears on both sides. So potassium is a spectator here because it appears on both sides. Chlorine is a gas on this side, and it's in its ionic state on this side, so it's not a spectator. So this would be the net ionic equation if you don't include the potassium. So that's done. And it says write the oxidation and reduction half reactions for the equation. And I'm just going to quickly do this. You can write it out properly, but I'm just going to join them like this. There is chlorine goes from Cl2 to Cl minus. So that represents a gain of 1 electron per chlorine, but it's 2 electrons total. And that makes it gain electrons is a reduction, so that makes it a reduction. And the iodine goes from I minus to I2. It loses 1 electron per iodine, and there are 2 iodines, that's 2 electrons total, and it's the reduction. So you could pull out those 2 half reactions and write them out separately like this. Chlorine 2 plus 2 electrons yields 2 chlorines, and 2 iodines gives you iodine gas and 2 electrons when they lose those extra electrons. Okay, and then this one was the reduction, and this one was the oxidation. It says identify the reactant oxidized and the reactant reduced. So chlorine was reduced, and iodine ion, iodide, was oxidized. Okay, now there's another way we can do this. And in chemistry, we have a way of keeping track of electrons that are moving. And we do that using something called oxidation numbers. Oxidation numbers are not charges, even though they are numbers that have a plus and a minus sign with them, but they're not charges. They're used for electron bookkeeping. They represent what charge the atom would have if both of the electrons in the covalent bond belonged to the more electronegative atom. So if you had, say something like carbon dioxide, oxygen is a more electronegative atom, so the electrons that are being shared in here would tend to go towards the oxygen, even though they're not really on the oxygen. So it's kind of like a partial transfer of electrons. But we can kind of still keep track of what that means and where the electrons have gone using something called oxidation numbers. Notice that oxidation numbers are like math numbers. They have the positive and negative sign in front, whereas ionic charges have the positive and negative signs after the numeral. So oxidation numbers are like our math numbers. Here are the rules for assigning oxidation numbers. If you have a neutral atom, the sum of all the oxidation numbers should equal 0. So if one of the atoms is a 2+ charge, the other one's got to be a 2- charge to cancel those two charges out, or those, two oxidation numbers out. If you have an ion that has a charge, like a polyatomic ion, the sum of all of the oxidation numbers should equal the charge on your polyatomic ion. And your polyatomic ion is, all of them are listed on your periodic table. So, for instance, if you have the nitrate ion that is NO3 1-, the sum of the oxidation number that you give to the N and to all of the O's should equal that charge on your polyatomic ion. Any element that you have, anything in its elemental state, has an oxidation number of 0. So there's a few ones that you kind of have to commit to memory, but if you work with these, by the time you finish this worksheet, you will have this next chart. You will know exactly what you're doing with this next chart. So here are the rules. These are listed in your textbook. This is on page 603 of your textbook, a version of this. First of all, an atom has an oxidation number of 0. That's not on this table. Anything that's a group 1 element has an oxidation state of +1. Anything that's a group 2 element has an oxidation state of +2. So group 1 elements like sodium and potassium, they're +1, just like their charge, believe it or not. Group 2, calcium, magnesium, they have a +2 oxidation state. These others are a little bit wonky. Hydrogen is almost always +1, unless it's in a hydride. So it's +1 when it's attached to something that's a nonmetal, and it's -1 when it's attached to something that is a metal hydride. Okay, like calcium hydride. So then it would be -1. But most often it's +1, like its charge. Fluorine is always -1. There are no exceptions. Oxygen is 99% of the time -2. The only time it's different is if it's attached to fluorine, or it's -1 when it's in hydrogen peroxide, H2O2. Then it's -1. So honestly, 99% of the cases is going to be -2. And chlorine is going to be -1 unless it's bonded to fluorine or oxygen. Sometimes it changes. So what we can do with oxidation states or oxidation numbers is figure out if electrons were gained or lost, depending on if our oxidation state got more positive or got more negative. If it gets more negative, it gained electrons. If it gets more positive, it would have lost electrons. So that's what we're going to do. So keep this table handy. This is page 603 while we work through a couple of examples. So there's a worksheet specifically for this, for assigning oxidation numbers, as well as the textbook questions on page 604. Once you're done this, you pretty much are ready to, oh no, there's one more little thing before you can do the quiz on 9.1. All right, let's look at the, let's leave one. Let's do number 3 first. We'll start here, number 3. Here's carbon. Carbon there is in its elemental state. And because it's in its elemental state, carbon has an oxidation state of 0. Okay, let's look at oxygen. O2. This is oxygen in its elemental state, so it also has an oxidation number of 0. Let's look at number 5 here, sodium chloride. The sodium in sodium chloride. Group 1 elements always have a 1+ oxidation number. So if sodium is 1+, this chlorine has to be 1- because they have to cancel each other out and get to some 0. So the Na here is 1+. Let's try the C in CH4. So we don't have any rules for C on our table, but we have rules for H. Every H was -1. And in this case, there are 4 of them. So what should the C be in order to make this whole thing 0? The C has to be +4. Because each H is -1 and there are 4 of them. So there's a sum of oxidation numbers of -4. So the C has to be +4. Each hydrogen is -1, but there are 4 of them. All right, let's try the Mn in MnO2. So Mn didn't have a rule, but O had a rule. O is always -2. It's -2, but there are 2 of them, so that's a total of -4. What does the Mn have to be to make this sum 0? Well, the Mn has to be +4 to make that sum 0. Let's try the N in N2O3. So the O is always -2, unless it's in peroxide, but there are 3 of them. That's a total of -6 of an oxidation state. Now I've got N2. What does each N have to be to end up with a sum 0? Hopefully you said each N will have to be +3 because there are 2 N's. So if the first N is +3 and the second N is +3, that makes a total of +6. And then that cancels out the -6 by all those oxygens. So you sort of figure it out like that. Now let's do sulfur. Sulfur is in SO3 2-. So the sum charge here has to be 2-. Oxygen is -2. There are 3 of them. That's a -6. What does the sulfur have to be in order to leave behind a -2 charge? The sulfur has to be +4. Okay. We can just kind of work our way through it. Now I'm going to look at this one outside of the S in H2SO4. This is an ion. This is actually H+ and SO4 2-. Okay, that's what's happened here. So when you assign the oxidation states to this part, you have to leave a -2 oxidation state, a sum of -2. So oxygen will be -2. There are 4 of them. That's a total of -8. Sulfur has to be +6 in order to leave the -2 on this part of the polyatomic ion. And of course, each hydrogen is +1, and there are 2 of them, so that gives us the sum of 0. So in this case, the S was +6. Okay, there's a bunch more questions in your textbook. Hopefully those make sense. Pause this right now and give that a shot. And here is a fill in the blank. You can give this a shot as well. Write oxidation numbers for this equation and try to solve it. You can pause it right now, and I'll go ahead and solve it. Hydrogen is 0, chlorine is 0. Hydrogen is +1, chlorine is 1-. That sums to 0, so we've got some changes. Hydrogen went from 0 to 1+. So obviously something happened. If it goes from 0 to +1, it got more positive. So that means it lost an electron, right? Loses 1 electron per hydrogen. Chlorine went from 0 to -1. It got more negative, so it must have gained an electron. And that's how you use oxidation numbers, because if your oxidation number gets more positive, so kind of gets bigger, then you're losing electrons because your number is getting more positive. If your oxidation number is getting smaller, more negative, you're gaining electrons because it's getting more negative charges. So hydrogen lost electrons, so lose electrons is oxidized because its oxidation number increased. Hydrogen atoms have partially lost electrons. Chlorine is reduced because its oxidation number decreased. The chlorine atoms have partially gained electrons. So these are covalent bonds, and so they don't fully gain the electrons. Now, hydrogen in this case lost electrons. It got reduced. If it got reduced, it caused chlorine to get oxidized, so it is also the oxidizing agent. Chlorine got gained electrons. Oh, sorry, hold on a second. Hydrogen lost electrons. I wrote the wrong thing. Whoops. Hydrogen got oxidized. It is the reducing agent. Sorry. And chlorine is, chlorine gained electrons, therefore Okay, so the chlorine here gained electrons. So gain electrons is a reduction. So it was reduced. Therefore, it caused something else to get oxidized. So it is the oxidizing agent. Okay, whatever got reduced is the oxidizing agent. Whatever got oxidized is the reducing agent. Great. Here's another practice question you can do. Otherwise, you can do the questions out of the textbook, which are on page 605. And you can try the worksheets from 9.1. Let's try one of these. I don't know. What's the first one? Identify the entities that are oxidized and reduced in the following reactions. So we already did that first example. Let's try this one. Iron solid and oxygen to iron 3 oxide. So Fe plus 3O2 yields FeO3. So this is a little bit complicated. What we're going to do is use oxidation numbers to identify what was oxidized and what was reduced. So here's iron. It's in its elemental state. I'm going to write the oxidation numbers above it in red. That's what your textbook does. So iron is at a 0. Oxygen is also in its elemental state. It's at a 0. Now on this side of the equation, when oxygen is part of this molecule or part of this compound, it has an oxidation state of -2. But there are 3 of them, so we have to account for a -6 total a total oxidation state. I have 2 irons here. What does each iron have to be to make this cancel out, this -6 cancel out? My iron total has to be +6, which means each iron has to be +3. So these are all my oxidation numbers across the top. And this is my rough work for figuring out the 0 sum. So its oxidation state is -2, but there are 3 of them. So we have to kind of account for -6. But oxygen's number is not actually -6. So let's figure out what happened. Iron went from 0 to +3. Went from 0 to +3. So therefore, did it gain electrons? Did it get more negative? No, it must have lost electrons, right? So if it loses electrons, lose electrons is a reduction, right? So we're looking at a reduction here. On the other hand, oxygen went from 0 to -2, got more negative. So it went from 0 to -2. It gained electrons. Oh my gosh, listen to me. Lose electrons, oxidation. Lose electrons, oxidation. This is oxidation. I'm sorry. Forgive me. The dog was barking. So it lost electrons. Iron lost electrons. So lose electrons is an oxidation. Leo, the lion, goes first. Oxygen went from 0 to -2. It got more negative. It gained electrons. That's a reduction. Gain electrons is a reduction. So this was the reduction. And therefore, oxygen is the oxidizing agent, which makes sense because oxygen. Iron is the reducing agent because it got oxidized. So it is the reducing agent. Okay, so you can try some of those. And that's the end of 9.1. You can go over some of the questions in the textbook and then try your 9.1 quiz.